Hello everyone, welcome back. My name is Mr. Cobalt, and in this video I'm going to show you how to write a molecular, complete, and net ionic equations for weak and acid bases. In this particular video, we're going to look at calcium nitrite with hydroiodic acid, and that's going to make a weakly conductive solution. And let's get into this. So this is a slightly different problem than the one I did earlier. So last time I did calcium nitrate with hydroiodic acid. This time we're going to do calcium nitrite with the same acid, and we'll see what happens there and what's different. Okay, so everything's the same as before. Again, we're going to write our calcium nitrite. So calcium nitrite is calcium plus the nitrite ion. And again, we want to recognize this as an ionic substance. And so you'll notice that we have the names of these substances that we're reacting. So we need to go to the formulas. And so if you are rusty with that and you need help with that, please see my video on naming acids and naming ionic compounds where I go over that. But I'm going to kind of go over it here too. Um, so we have calcium nitrate. So since this is an ionic substance, the two names of the ionic substance are the names of the ions that make up the substance. So we have calcium and we have nitrite ion. So we have the calcium ion, which is a +2 charge. And so we know that's a +2 charge because it's in group 2. And so there's a couple of ways to know what the charge is of your main group elements. If you're in groups 1, 2, and 3A for the main group elements, then the charge of your ion is going to be the same as the charge on your the charge of your ion is going to be the same as the number of the group that you're in. Okay, and so since we're in group 2 here, then that's going to be a +2 charge. The other way to do it is to think about the valence electrons and the fact that all atoms want to be like a noble gas and have that outer shell, that full outer shell. Since calcium is in group 2, we know that it has 2 valence electrons because the number of valence electrons is equal to the number of the group that you're in for the main group element. So 1A elements are going to have 1 valence electron. 3A elements are going to have 3 valence electrons. So since calcium is in group 2A, then it's going to have 2 valence electrons. And so that calcium can lose those 2 electrons to have a noble gas configuration, to have a full outer shell. And so that's going to lead to the 2+ charge, because once you lose those 2 negative electrons, you now have 2 protons in your nucleus that are no longer being balanced by the negative electrons. So that's going to give a 2+ charge. Nitrite, that's going to be NO2-. That's a polyatomic ion. You have to know your polyatomic ions. You have to memorize the formulas and the charges. I'm sure your teacher gave you a list to memorize. I have a video on polyatomic ions, so you can go to my video and watch that. And in that video, I give you some strategies and patterns to help you learn those polyatomic ions. So here I have the ions now, and so now all I need to do is put them together, and I need to make sure that the charge is balanced. So I have a 2+ charge here, I have a negative charge here, so I need 2 nitrite ions to balance the charge on my calcium. The other way I could do it is I could do the crisscross method. So I have a 1 here, so I could put that as a subscript there, and I have a 2 here, I could put that as a subscript there. We don't write the ones, so it's going to be just Ca. And then I have 2 nitrite ions. So anytime you have more than 1 polyatomic ion, you're going to need to use parentheses. So here I have the nitrite ion in parentheses, and I have the 2 on the outside. If you only have 1 polyatomic ion in your formula, don't use the parentheses. All right, so now I have hydroiodic acid. Again, I know that this is a binary acid instead of an oxyacid because of the fact that it begins with hydro. So that tells me that there are two elements in my acid. One of those has to be hydrogen because it's an acid, and the other one is indicated by the rest. So hydro indicates hydrogen, so that's one of your elements, hydrogen. The other one is indicated by the rest of the name. Iodic is referring to iodine, so iodine is the other element, so Hi. And iodine typically has a 1 minus charge, so I would need one H plus to balance that, so Hi. Okay, so now that I have these two reactants, now let's make the products. So how do I figure out the products? So right away, you should notice that this is an ionic substance. And although this is technically not an ionic substance, it is a molecular substance. It can ionize into ions. So we could treat this like an ionic substance. So whenever you have two ionic substances or pseudo-ionic substances, you could treat that as a double displacement reaction or double replacement reaction. And the way you figure out the products from a double displacement reaction is you take the inner ions, they will go together. So the H plus and the nitrite ion will go together, and the hydride and the calcium will go together, and that will form your products. So all you need to do is make sure that when you write your formulas for the products, balance the charge. So here I have a +2 charge for the calcium. I have a -1 charge for the iodine. So I'm going to need two iodines to balance that charge. So it's going to be Ca2. And so here I have the H plus and the NO2 minus is going to go together. So that's a 1-to-1. So there, I only need one each to balance the charge. So that's going to be HNO2. So now I have my two products. Now all I need to do is balance the charge and figure out what the states of matter are. So here I have one calcium. Good. Here I have two nitrite ions. I only have one nitrite ion there, so I'm going to need a 2 coefficient in front to balance that. So now I have two nitrite ions on both sides. Here I have one hydrogen, but now I have two hydrogen on this side, so I'm going to have a 2 coefficient there. And now I have two iodides and I have two iodides, so that's balanced. So now I have a balanced equation now for the states of matter. So here I have a nitrite. Nitrite, I can look on my periodic, on my solubility rules here. And it says that all salts of nitrates and nitrites are soluble. So really there's no exceptions. So this is going to be aqueous. So that's aqueous. Hi is a strong acid. And again, the difference between a strong acid and a weak acid is that anytime you have a strong acid or a strong base, that means that it's going to dissociate completely in water. So you're going to have none of this left over, or very, very, very little of it left over. Most of this is going to be in H plus and I minus ions. So H plus and the iodide are going to be separated in water, completely floating around by themselves. So you're not going to have any Hi together floating around in water. So this is going to be aqueous. Here we have calcium iodide. And so the rule for calcium iodide, if we read that, is going to be all chlorides, bromides, and iodides are soluble except when you have silver, or when you have lead 2 ions, or when you have your mercury 1 ion. We have calcium, so that doesn't apply. So that's not an exception. So this is going to be soluble. So this is AQ. And then this here, that is HNO2. That is your nitrous acid. So we formed nitrous acid, which is a weak acid. And that is really important to keep in mind when we're doing our ionic equations, like our complete and our net ionic equations. We have to realize that we made a weak acid. And again, what do we mean by weak acid? So again, strong acid is where everything completely ionizes, the ions separate, and they're floating around. You don't have the molecule together. For weak acids and bases, very little of it will ionize or dissociate. So most of it, almost all of it, will stick together. Some of it will separate, but most of it will be together, floating around. So since this is a weak acid, nitrous acid, that is going to be stuck together for the most part. So this is really not going to dissociate all that much. So that is important to keep in mind. But we're still going to have this as aqueous, because even though it's together, it's still dissolved in water, right? So this is aqueous. Okay, so now that we have our balanced molecular equation, so here's our balanced molecular equation. Now we need to do our complete ionic and our net ionic equations. So for the complete ionic equation, we're going to take everything that is aqueous and we're going to separate it into ions. However, we need to keep in mind that even though this is aqueous, this is a weak acid. So we're not going to take that apart because almost all of it is together. So this is going to stay together as it is. Okay, we're not going to separate it into its ions because again, that's a weak acid, and so we're going to keep that together. But this is an ionic substance, so that's going to separate into its ions. This is a strong acid, that's going to completely separate into its ions. And this again is a soluble ionic substance, that's going to separate into its ions. So let's go ahead and do that. So here, the calcium, Ca2 plus aqueous. And notice that when I am separating the compounds into their ions, I am writing the charge down. We don't write the charges when we write them together in the formula, but when we separate them, we write the charges. So here, I have two nitrite ions. So the two nitrite ions are going to be separated. I'm not going to write the subscript. The subscript actually becomes a coefficient. So I'm going to write the coefficient 2. And the reason is because if we carry the subscript, that would be like saying that the two nitrite ions are together, bonded, and they stick together. And that's not what's going on. So the 2 here merely tells me that I have 2 of these ions that are needed to balance the charge on the calcium. So I'm going to write, whenever you have a 2 subscript representing the number of ions, that becomes a coefficient. So I have NO2 minus aqueous. And then I'm going to break this apart. So I have 2H plus aqueous, and I have 2I minus aqueous. And that is our reactants. And so I'm going to do the same thing for our product. So the calcium iodide, that's going to break apart. So I have Ca2 plus aqueous, and I have 2 iodide ions. So remember, the 2 subscript becomes a 2 coefficient. So 2I minus aqueous. And then I'm going to keep this together. So that's going to be plus 2 HNO2 aqueous. And again, the reason I'm keeping this together is because that is a weak acid and it stays together for the most part. Okay, so this would be our complete ionic equation. So complete ionic equation. So now to make the net ionic equation, we need to pull out our spectator ions. And what are the spectator ions? The spectator ions are the ones that are not doing anything. And so here's where we need to be careful with the weak acid. So we need to, again, recognize that we have a weak acid here because that's going to affect how we write our net ionic equation. because that is not coming apart. So what we could do is we could look at what ions participate in the formation of our product. So here the product is HNO3, so we could pay attention to that and see, well, H plus and NO2, I'm sorry, I said NO3, but that's NO2. So we have H plus and NO2 participating in that. So everything else, the calcium and the iodide, is not participating, so we could get rid of those as a spectator ions. The other way you could do this is look at what is the same on both sides, what doesn't change, and anything that stays exactly the same on both sides is a spectator ion. So here we have calcium 2 plus aqueous. Here we have calcium 2 plus aqueous. That stays the same, so that's going to be a spectator ion, so we could get rid of that. And the nitrite ion, notice that's aqueous over here, but then it becomes part of the product over here. So that is not a spectator ion. Same for the H plus ion, but the two iodide, I have two iodide aqueous ions here. I have two iodide aqueous here, so no change. So that is a spectator. And so we write what's left. So here I have two NO2 minus aqueous plus 2H plus aqueous, and that's going to form 2HNO2 aqueous. And so you can see here, this is our this is our net ionic equation. Let me erase that so we make it better. So our net ionic equation. And so what you can see here is we have two nitrite ions, two H plus ions. They're going to come together and form a non-ionic substance. So here you're going to have mostly this. So in reality, there's a little bit. So this is kind of a reversible reaction. Some of this can become H plus and NO2 minus, but very, very little of it will. Most of it is going to be in this form. So maybe if we do a double arrow, we have a larger arrow going this way and a smaller arrow going this way. So some of this is going to be in solution, a little tiny bit. Most of it is going to be in this solution. And remember, this is a molecule. It's not an ionic substance. There's no charge here. So this would explain why it's weakly conductive solution. Why does this make a weakly conductive solution? Well, in order to have a very conductive solution, you need a lot of ions in solution to allow for that flow of charge, right? So if you don't have a lot of ions to move around, it's not going to be very conductive. But here we're going to have a little bit of ions in solution, so it's going to be weakly conductive. Most of it is going to be in this form because, again, it's a weak acid, so this is not going to ionize very much. I hope that's helpful. I hope that makes a lot of sense. Let me know if you need any more help on this. If you put a comment in the comment section, let me know what you think. If you have any questions, if you like this video, if this is very helpful, please make sure you like the video, hit that like button, subscribe to my channel so you could get more notifications. There's a notification bell, hit that, and you'll be notified by any videos that I put out. Thanks for joining me, and have a great day.